microprocessor, and one is called microcontroller. And how are they different? Okay, microprocessor is an early version of microcontroller. I'm going to talk about this in detail. And so then we talk about the components of microcontroller, and just like in our brain, we have a lot of different components, right? So this is the same thing. Understand the CPU, and CPU is architecture is the part of brain, and data bus and the address bus, memory types, and addressing. And finally, I will show you the basic stamp system. And so this is a very, very compact economic. This is mechatronics system. It was used for this class about 8 years ago, but because there is the renovation of this system, change or modification of this curriculum. So this is a step system and was removed from our this class. So we only focus on PLC and industrial robots. Okay, but I want to tell this one is a very, very good example and to illustrate what this mechatronic system looks like. So here is the microprocessors and versus these microcontrollers. Microprocessors, so microprocessors, this is in 1960s or 1970s. It is many, many years ago. These microprocessors, and they are a CPU on a chip at the very beginning, a CPU on a chip. The fundamental components such as program and data memory and parallel input and output, along with communications peripherals, are all physically separate from the microprocessor, and the microprocessor must be integrated with separate components to form a microcomputer or single board computer. All operations and tasks require interaction with external components. I'm sorry, this is the width, right? So any questions with regard to this one? You want, in a nutshell, microprocessor is just a CPU at the very beginning. All other components, all other necessary components, they are separated physically from the CPU. If you want to have a standalone functioning system, you must have a CPU itself and all other necessary components. So that's the reason this is really important. This in 1960s, 1970s. The single board computer. Very single board computer. So on the contrary, microcontroller, as the technology evolves, the things change a lot. Right? So you can see, as people integrate the CPU and all other necessary components in one single chip. So this is called microcontroller. So with everything else necessary to create a single chip computer, at a minimum, it requires ROM. ROM means read-only memory. RAM is randomly accessible memory, I/O input, output, and a clock source. So even for this one, the clock source, there is no clock on the CPU. You should have your own clock. So microcontrollers are intended for standalone, single-purpose systems, and they are also called single-chip computer. Maybe in the exam one or this is quiz one, I will ask you guys to use your own language to tell me what are the differences between the microprocessor and the microcontroller. You should be able to use your own language to tell me, right? Questions? So these three, they are related, but one is a really important. This is at the very beginning. We have microprocessor. As the technology evolves, and we have a microcontroller. When I was a student, I worked on the microprocessor, and then I worked on the microcontroller. I have had a hands-on experience with both of them. I was a student in the early 1990s, 40 years ago. You can imagine how, right? Always you cherish this golden area now, the golden age now. This is microcomputer architecture. So this is microcomputer. architecture, just like the brain, when we do the anatomy, in other departments, and they will show people what the brain is made of, what is the components of the brain. Now we are showing what is the microcomputer. So we have this is the CPU. Okay, this is the CPU, and we have what CPU. We have control unit and data registers, ALU, instruction decoder, instruction register. So this is called microprocessor. Okay, so this is called CPU. And so here is the memory. We have random accessible memory, read-only memory, EP programmable. This is called electrical program read-only memory. Okay, electrically programmable read-only memory. And so this external I/O, AD is analog to digital converter, DA digital to analog converter, ED this is a enhancer, this is enhancer, this is performance enhancer from digital to digital. And so here is a switch, and the switch we have connected to the sensors and actuators. So this is the math memory, or this is internal memory, but you can have the math memory, disk, tape, and CD-ROM. And here are the system I/O, keyboard, printer, monitor, modem, network devices. So how are all these components, they are related? How these guys communicate with one another? So here are the bus. Okay, so here is a data line, the bus, the data line, address lines. So the data bus, we call this the data bus, and we call this address bus. And we also here called control bus. We have three different kinds of buses. One is called data, send all the data. Second one is address, and third one is control. You know bus, right? Yeah, you took bus when you were young kids. Do you? Okay, so the bus means the transport these kids from home to school and vice versa. And so here is also these buses, they transfer this either data or address or the control from one destination to another. This is called bus. So this ALU stands for algorithmic logical unit. This ALU. Questions regarding this slide? Questions regarding this slide? So ALU stands for arithmetic logic unit. Arithmetic logic unit. We have one ALU in our mind, in our brain. Right? Otherwise, you cannot calculate. You cannot do any math problem. Arithmetic logic unit. We want me to write down? Arithmetic logic unit. So this is EPROM, EPROM. This means electrically programmable read-only mode. Right? They will have a new program, and you can electrically erase the previous the existing one and send all you write a new one there. So here, this is the simplified version of microcontroller. So we have program memory. So this is the program memory. ROM, EPROM, EEPROM. This I'm going to talk about one by one. Data memory, RAM, and CPU, and I/O, and clock source. And for each of these systems, we have a clock. We have a clock. Do you guys agree? On the computer, you can see the time, right? You can read the time. That's the clock. What is the clock? Functionality of the clock. A clock is used to synchronize all these components. So as the biological clock in our body, have you guys ever heard of the biological clock? Each of us has our own biological clock. Our own biological clock tells us when we should get up, when we should go to bed, when we should take a nap, when we should take this snack food. Do you agree? You must follow the your own biological clock. Otherwise, you will feel very tired. Right? The same thing here. This is a clock is used to synchronize all these different components in the system. So these are clock source, central processing unit, CPU, program memory, data memory, digital input and output. So here's output. They are used to control some actuators. These inputs they are used to get some info from our environment. So these are connections to the external peripheral components. So this is a simpler version of a microcontroller. So here is a typical full-featured microcontroller. There are a lot of acronyms I want to tell you guys one by one. So even though so this is a CPU, right? This is a CPU, and the RAM is a volatile data. Volatile data means that use it when the computer is on. When you turn off your computer, the data is disappeared. It disappears unless you save it. Okay, so we have ROM, EEPROM, EEPROM. This is the ROM, electrically programmable read-only memory. So EEPROM means electrically erasable program read-only memory. So here are 1E, electrically programmable. If we have another E, then second E means electrically erasable programmable controller. So here's the timers. We have timers here. We have digital I/O ports, and this includes switches, on and off sensors, external analog to digital converter, or digital to analog converter, digital disciplines, on-off actuators, series communication, serial communication, and we have several different kinds of serial communication. So you do not need to memorize all these things. Okay, you can just have know them and what they are. You don't need to memorize them. So because it's too old, okay, I just want to tell you the history. It's too old, and you are next generation has don't need to memorize all this. Okay, so SPI means serial peripheral interface. SPI, serial peripheral interface. So this is I want to show you more things. SPI, and this stands for serial peripheral interface. Of SPI. The four communications. This is I square C. I and square C. I square C stands for inter-IC bus. So this is the integrated circuit. Integrated circuit. This is the communication. or this is integrated circuit. So this is I square C. Next one is UART. UART stands for Universal Asynchronous Receiver and Transmitter. Universal asynchronous receiver and transmitter. So this is UAT, UART, and use ART. And use ART, and this is I means, and this S means the synchronous, and this is post synchronous. Synchronous and asynchronous. And receiver and transmitter, and US ART. So this for communications. For communications with either external and PR1 or other microcontrollers, and maybe the host computer. So AD means analog to digital converter. Analog sensors have analog sensors. For example, potential monitor, and this is monitor the voltage. So all this is analog. But if you want to control all these variables, you must have analog to digital converter, because computer can only handle the discrete signals. That means digital signals. For DA, after you finish this is any kind of algorithms, and then you decide to take some action to do something, and you need to use digital to analog converter to convert the output digital signals into the analog signals that are required to drive. This is either analog actuators, amplifiers, or analog displays. So now currently, and there are a lot of actuators that are driven by using these digital signals. If this is the case, you do not need to have the DA. Maybe you still need to have D/D, right? Because the power is different. Questions regarding this slide? No question? And then we talk about CPU. On CPU, we have four most important components. One is a control unit. And the control unit contains circuitry that uses electrical signals to direct the entire computer system and to carry on or execute and store the program instructions. It's a control unit. And ALU stands for the arithmetic logic unit, contains the electronic circuitry that executes all arithmetic and logic operations. So ALU. And then we have registers. Registers, they are temporary storage area for instructions or its data. And decoder, and decodes the instruction and decides what it means. It's a decoder. Because the computer itself can only execute the order and carry out the order that is written in the 1010, this kind of binary numbers. If you say something, and you must have a decoder, okay, to convert your language, our language, programming languages into the machine language. Machine language is 0, 1, 0, 1, this kind of thing. That's a decoder, what the decoder does. Questions regarding this slide? So this is basically and the components for our brain. So then we talk about the data bus, address bus. So the data bus is used to communicate words and to and from data registers in various system components such as memory and CPU interface. Input and output peripherals. Address bus is used to select the devices or specify the data locations and within memory. So this one is for the data, and this one is for the address. Why we need to have an address? Because a system or functioning standalone functioning system, and it might have many components. If you want to send out the data, the system wants to know where you want to send the data to. That's guys? You want to send the peripheral 1, component 1, or you want to send this data to the actuator 1, or want to send it to the displayer 1. You must specify the address, and then you send out data. Does that make sense? Also, when you want to retrieve the data, you also need to specify, I want to know the data in this unit, in this address. Address first, and then get out the data. Or address first, then send out data too. Just like a big hotel, because you have a lot of guest rooms, right? If you want to find someone, you must know which room this guy is living in. You agree? Otherwise, you need to search from search all these. Okay, the control lines transmit the read and write signals, the system clock signals, and other control signals. The system interrupts. So these are system interrupts. We are going to talk about this interrupt. Have you guys ever heard this concept? Interrupts. Excuse me for my interruption. It means that something you stop something, right? So here is the same thing. Interrupts means that when the system is running, if something happens, this is a program must be stopped. So this is called interrupts. And underscore this one, right? Underscore this one. We will use this one when we program PLC, when we program industrial words. Interrupts. So this is a data bus, address bus, control bus. And then we talk about the memories. There are a lot of different memories. We are familiar with RAM, and we talk about RAM, randomly accessible memory or random access memory. So this volatile loses contents of the power external. RAM read-only memory is non-volatile. So that means when you turn off the computer and this is still there. For example, the Microsoft, this is an operating system, the data is still there. Otherwise, you'll be in trouble, right? So EPROM is called electrically programmable read-only memory, and EEPROM, electrically erasable programmable read-only memory. So this is relatively they are non-volatile, okay? But you can still use some device to erase the program, and then you write this new program. Either this is volatile or non-volatile. It's just a relative word. Okay.
So then does it gear up ROM and EEPROM, and then if you upload code to the EEPROM, does it erase it?
Yeah, you need to erase it. You need to use erase. That is 30 years ago when I did my master's degree. I used this. There is a ultraviolet device, and you put your chip into the device. Okay. After 15 minutes, the bird chirps. The bird chirps tells you that this erasing task is finished. and then you can just write your own the new program. But I do not know what kind of devices people are using now to erase and write this old program and this new program respectively. Because now I'm working on the FDM, I'm the SolidWorks guy. I do not. I'm still working on the control. This is microcontrollers, but not too much. Okay, guys. So this is just a relative word, non-volatile and volatile, and all of them they are strictly speaking they are volatile. And we can use any ways to erase the existing programs and then create our own new program. Okay, so sometimes for this one, EEPRM, they use high voltage than the microcontroller voltage may be required. So this, I just show you guys, you can have this, actually this one is the same, I think. Okay. And then we talk about this is memory. And memory are used to store the data. And first you must have address, and you need to allocate the address to all this data. So this figure shows the address space organization, and each address corresponds to a unique location and in memory. Okay, so memory means we say the memory, you can just think this memory card is just a big hotel. This big hotel has a lot of the guest rooms, and you need to select where you want to write this data. Which guest room you want to write this data. So each address corresponds to a unique location that we say the guest house, guest room in memory, which contains data. Data can be numbers, configuration, or other numerical quantities. It can be numbers, configuration, or other numerical quantities. You need to know to be very clear that the digital, this is the decimal number we are using, and that's for our human being only. Okay, the computers does not recognize 10. Right? We are using the base 10, right? So this is the number, decimal number, but the computer for the address, and we use hexadecimal or the base 16 number, which will be discussed in later class, in next class. So this one, hexadecimal, is HEX. HEX is based upon binary number system. You know binary number system, right? 0, 1, 0, 1, these kind of things. But this is a hex is based upon that one. So look at here, this is the address, okay? So you can write down, maybe you can just write down as hexa number, it is the base is 16. See, from 0 to 9 is similar to our decimal number system. But after 9, we will have A, B, C, D, E, F. A corresponds to our number 10, and B corresponds to number 11, and F corresponds to number 15, right? Remember that, guys? Number 15. After 15, this is 16. Because this is base 16, when it becomes 16, and you must have this new one. So you can see come from this 1, this becomes 1, and this becomes 0. So this is the base 16 number system. So A stands for the 10. A corresponds to our decimal number 10, and so on and so forth. F corresponds to decimal number 15. So this is the address, and then this is the contents. So this is the guest house number. So this is your guest, and who is in which room. So this is this figure presents a typical memory map. So here is this block, okay, address block. So this is I can use this one as the registers. So here is from 0800 to 0FFF. This is I use as RAM. From here, I reserve it. For here, from this gas room, I used as the flash EPROM and so on and so forth. This is very similar to the guest house, right? So I attend the conference. Usually, there's a conference hotel, and they have some. They reserve some the guest rooms for the conference attendees. It's very similar to the guest the hotel. It shows the range of addresses used for different purposes: program memory, data memory, control registers, along with the interrupt vectors. This is interrupt. You have some idea about the interrupt. Questions regarding this slide? No question? Okay, the other subsystems, we have control registers, we have ports, and the parallel interface, this input and output. The counters, we have counters. All the system, all these microcontrollers, they have counters and timers. And PLC is one specialized microcontroller. But as the serial input and output, analog to digital converters, digital to analog converters. So this is other typical subsystems for your standalone functioning microcontroller system. Then we talk about the bus architecture. So I want you guys to know this, okay? So there are two different architecture for parts for the system, and you should know. I want you guys to know the difference between them. I will ask you. So one is called von Neumann. This architecture. Von Neumann architecture, it says that in the microcontroller system, all the components in the microcontroller system, they are sharing the same data bus and address bus as they perform tasks and communicate with each other. They are sharing data bus and address bus. So this is one example. The free skill, this is MC, this one. So this is a very early of. So definitely, Professor von Neumann is a talent professor. He just opened this channel for us, opened this area for us. This is CPU. You can see the CPU, and so these are different. These components, we have data bus for all of them and address bus for all of them. So this is architecture is named von Neumann architecture. So, but this architecture has some shortcomings. Right? Shortcomings. Then, there's another professor called Howard, and he designed a new. This is architecture. So, in the Harvard architecture. So this this kind of microcontroller and the program memory and data memory do not share the data bus and the address bus. And that means these two guys, and they are using their own data bus and own the address bus. And this eliminates the traffic jam encountered in von Neumann architecture. So a Harvard architecture microcontroller can be much faster for given circuit complexity. So these are two examples. So this is the Harvard architecture. So this is called von Neumann architecture. In either the exam or the quiz, I will ask you guys, and please close your eyes. Tell me the difference between the von Neumann architecture and Harvard architecture. Okay. This is the history, kind of this is the history of this microcontroller. And questions so far about the differences between these two different architectures? Both the von Neumann, Professor von Neumann and Professor Howard, they are talents, they are genius. Questions? No question. Then we talk about our. This is the basic step 2 microcontroller used for mobile robot. So I still have these mobile robots in my office. If you are interested, I can give you one for fun. or play, but after the class is finishes, you return the file. Also, you can do some research for it. So this is the chip. This is microcontroller. You can see on this chip we have a lot of things. This is a CPU. This is the interpreter chip, basic. And so we have EEPROM. We have serial signal conditioning. We have 5-pulse regulator along with the resonator. And so we have this. You can see all these components. And most of these, all these necessary components, they are integrated into one chip. That's the reason this one is a microcontroller instead of microprocessor. And this is a bigger picture of this one, of this microcontroller. And then we talk about, and we have different pins. And different pins, we call these legs, okay? The legs, different legs. So you need to connect to these different legs to the different components. From here, this is S out. Pin 1 is S out, and pin 2 is S2, and pin 3, and this is ATN uses the serial DTR line to get the stems attention for programming. So from here, 5s to 20s, the pins, and their input and output pins. So here is 24 volts. This is pin 24. I'm sorry, this is pin 24. This is the power. Right? This is the power. So here is the ground. This is the ground. This is driven by the DC. Okay. So DC will have 2 terminals. Terminal ground. You need to connect here. And this is a positive terminal cathode. You need to connect here. So here is RES reset. Pin 22 reset. And so here is VDD. 21 is a VDD. So here is a regulated 5 volts. This is a regulated 5 volts. And so here are different kinds of the basic stem. So these kind of chips, they are called stems, basic stems. They have different variants. So this is the earliest one. So this is the newest one. So we have they are different in terms of memory size and speed, along with additional features. So this one is one earliest one. So this one will be the cheapest. But this one can do a lot of more things, but it will be more expensive. So here is a bigger picture of this is the board of education on a ball board. This is the robot is called a ball board mobile robot. So this is the frame, and you can put the basic stamp, the chip on here. Right? So this is used to accommodate. This is a basic stamp. So here we have wall DC supply. You can have wall DC supply. However, you can also have a battery also. It's a 5 volts regulator. So here's the power on lights. When you turn on light, when you turn on the power, this light will be turned on. And so this will serial programming the port here. So here is a off module power, servo power. So this is, and you can just turn it off. You can in the middle. So this is a module power, and turn this way is servo power. And servo power is used to control the 4 wheels. So here's the servo connections. And so this is a power, and this power head here. And here is I/O header. This is I/O header here. So this is a breadboard. Okay, so this is a breadboard, and you can do a lot of things based on your needs. This is a breadboard. You can see this is a lot of holes you can play with this. So this one is a reset switch. So this is pretty much what we have today. Before you guys leave, I want to emphasize the several important points in today's class. So in today's class, I told you guys the difference between microprocessor and microcontroller, right? You should know that. You don't need to look at your lecture notes.